Hi, let's continue our discussion of evaluating stability of control systems by looking at the Routh-Hurwitz stability criterion. In the previous video, I said that if the poles of the transfer function, of a system transfer function, uh, if none of the poles have a positive real part, then the system is stable. Or positively, you could say that if all the poles of your system transfer function have negative real parts, then the system is stable. Now, of course, we also said that evaluating poles of third order and higher systems is very difficult, and that's where this stability criteria comes into play. Okay, so let's say for a particular system, we have the characteristic equation as given here. What is the characteristic equation? Do you remember that? A characteristic equation is the denominator of the system transfer function, right? So here we have a nth order characteristic equation, and we want to evaluate whether the system has is stable or not. And the stability is going to be determined by the coefficients an minus 1, and so on, right? So what we want to do is we want to first make something called a Routh array, and then at the end, so we'll learn how to make a Routh array, and at the end of the lecture I'll tell you how you can use the Routh array to figure out whether the system is stable or not. Okay, so the first step of making the Routh array is to make a table like this. Now let me explain how this comes about. So you take the highest power of s, the highest and the next highest power of s. So actually, let's not say next highest, just let's say just the highest power of s, and put it on the left hand side of this array, and write uh, Sn minus 1 here. So if this was s cubed, this would be s square, and so on and so forth. Okay, and then what we do is we write the coefficients of the powers of s on the right hand side of this equation. So the coefficient of s to the power n would go here. The coefficient of s to the power n minus 1 would go here. The coefficient of s to the power n minus 2 would go here. The coefficient of s to the power n minus 3 would go here. The coefficient of s to the power n minus 4 would go here, and then n minus 5, n minus 6, n minus 7, till we reach a0. Is that okay? So that's kind of the first step of the Routh array. So we are filling in all the coefficients. Now in some cases it is possible, let's say, that there is no s to the power n minus 1 term here in the characteristic equation. If that is the case, then an minus 1 is equal to 0. So you will put 0 at this place. Okay. So once we have done this, now what we want to do is we want to evaluate uh, we want to evaluate the next row of the Routh array. Okay, so how are we going to do that? So the next row of the Routh array would have the next lower power of s, right? We have n minus 1, and then you have n minus 2. So you want to find out this value b n minus 1. To do that, let's call this row as the current row. Okay, and once we've identified the current row, take the two rows that are above the current row. So we take these two rows. Okay, so they are just above the current row, and mark out the elements in the first column of those rows. So in this case, those are going to be an and an minus 1. Okay, so we've done that, and after doing that, identify the current column. This is the current column. Identify the elements in the top two rows uh, in the column immediately after the current column. So we are looking at an minus 2 and an minus 3 here. Okay, so those are the values. So you should have four values in the rows, in the two rows above the current row now. And once you get those 4 values, you just need to identify one more number, and that is the first number in the row that's immediately above the current row. So in this case, it's an minus 1. Okay. So once you get an minus 1, and once you get these 4 numbers, you can write bn minus 1, that is this number that we are trying to evaluate, as minus 1 over an minus 1, and the determinant formed by these 4 numbers, an minus 1, an minus 2, an minus 3. And of course, you would know how to evaluate the determinant, and therefore the bn minus 1 is going to be equal to this. Okay, let's try this one more time for the element which is going to go here. So that's bn minus 3. So this is the current row. We identify the 2 rows that are immediately above the current row, which are these two rows, right? And then we identify the 2 elements in the first column of those 2 rows. So those are going to be that. Okay. Now locate the current column and identify the 2 elements in the column immediately after it. So that's going to be those 2. So now you can use these 4 numbers to form the determinant. Okay, and of course the value of the determinant is going to be divided by an minus 1. So minus 1 over an minus 1 and the determinant formed by these 4 numbers. Is that all right? So we do this over and over again. So let's take another example. Let's look at the number that goes here. So if you have this number, so if you want to evaluate this number would be minus 1 over an minus 1 and the determinant formed by these 2 numbers and the 2 numbers which would be here. Okay, let's look at how you would find the value for Cn minus 1. So the value for Cn minus 1 is going to be minus 1 over Bn minus 1 and the determinant formed by 1, 2, 3, 4 numbers. So those 4 numbers. So Cn minus 1 is going to be this value. Okay, hopefully. And similarly, Cn minus 3 is going to be the determinant formed by these 4 numbers divided by minus 1 over Bn minus 1. And so on and so forth. You just keep filling up this array till you reach s to the power 0 here. Okay. And once you have reached s to the power 0 and evaluated the first element of s to the power 0, you have done all that you need to do. Now, once you have done that, what you can see how many times the sign of the coefficients here is changing. Okay, the number of sign changes is equal to the number of roots with positive real parts in the equation. Okay, let me repeat that. I'm just reading out from here. The number of roots of the characteristic equation which have positive real parts is equal to the number of sign changes in the first column of the Routh array. Now for stability, how many roots can have positive real parts? 0, right? So none of the roots should have positive real parts, which means that all these coefficients need to be of the same sign if your system is going to be stable. Okay, so that's what I've indicated here. So the necessary and sufficient condition for stability is that there are no sign changes in the first column of the Routh array. Hopefully that makes sense, and in the next few videos we are going to look at a few examples and hopefully they will help you understand this. I think the only way to get a handle of how to make Routh arrays is to do it over and over again.